Today we're going to introduce material. Well, last week we introduced material for Exam 4 from Chapter 6, chemical reactions, and we learned how to balance those reactions using my budget method. Today we're going to look at Chapter 7, and 6 and 7 are included on Exam 4, reactions in aqueous solutions. All right. These are the topics. And here we go. We can think of chemical reactions as being driven from reactants to products. And if we do that, then we can identify certain driving forces that favor the production of, that favor the reaction producing those products. One of the easiest to identify, if we're trying to establish the fact of a chemical reaction, one of the easiest driving forces to identify is the formation of a solid or a precipitate. So if we have something like silver nitrate in solution, and we add to that sodium chloride in solution, right? We know that in solution, these are separate ions. I mean, this is the formula, but in solution, they're separate ions, like that. So this chloride interacts with that silver, and this sodium interacts with that sodium, and we get sodium nitrate, which is still soluble, and silver chloride, which is not soluble. So that's the driving force for this reaction, producing solid. When you think of it in these terms, when you produce a solid, are the ions of that solid still available for this reaction? And the answer is very limited, but for all intents and purposes, they're not available anymore. So you can't get a reaction going the other direction. In other words, this drops out of the reaction medium and it forces the reaction to go this way to replace the solid that's being removed by precipitation. Formation of water is a good one also. If we have, say, hydrochloric acid and sodium hydroxide, both in solution, we know that we're going to get an interaction between the sodium and the chlorine. And that's soluble, right? Same example as this, plus water, which is considered a pure liquid. So this sodium interacts with that chlorine. This hydrogen interacts with the hydroxyl to give us water. And the formation of that water is very, very stable. It does not dissociate easily. So the fact that it forms this very stable compound pulls the hydroxide and the hydrogen ions away from the reacting side toward the product side, to be considered a driving force. Transfer of electrons. All right. Let's take sodium solid and chlorine gas, right? And that will form sodium chloride solid. Now, ask yourself, is that equation balanced? The simple answer is no. You got two chlorines here and only one there. So we need two to supply those two chlorines, and now we need two sodiums. So now we have a balanced equation. Electrons have been transferred, and we know that because this sodium chloride is an ionic solid with a plus and a minus. These are neutral. The chlorines and the sodiums are neutral. They have no charge. So how did they get over here to a charged state? They had to transfer electrons from one to the other. And what happens is we get a transfer of an electron, actually 2 electrons, one from each sodium to go to each chlorine. This is 2 lost from the sodium and 2 gained by the chlorine. And that establishes this ionic solid. That's a driving force, transfer of electrons. Formation of a gas. How about, let's see, I can put it down here. Say we put hydrochloric acid in aqueous solution, and we have zinc solid. Okay? Well, zinc is a very reactive metal. And when you put it in the presence of an acid, what we get is, let's see. Yeah. We'll get zinc chloride, which is in aqueous solution, and it's soluble. And then we also get hydrogen gas. So in order to make that come out, we need 2 here. 2 hydrogens, 2 chlorines, 1 zinc. The formation of that gas drives the reaction, and for a similar reason to the formation of a solid, only in the other direction, because the gas doesn't sink as the solid does, it floats. You get bubbles and they escape the solution. Now they're no longer available for a reverse reaction, and that drives everything to the right. So those 4 are primary driving forces for chemical reactions. Oh, I got a reactions which form solids. This little video, how long is it? I thought I could. Okay, we'll just watch.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. But there are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these 2 liquids. I have a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make 2 layers. So what I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so that they don't mix. Okay, so I think that's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. And they're actually making a solid. A solid material is formed where the 2 liquids meet. And what I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the 2 liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material, and it allows the 2 liquids to meet again, and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for our volunteer. You would like to stand there. Let's pop those on. What's your name?
Dylan.
Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. Now, when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia, and in a minute, that brown colour should disappear. There, now it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that, and I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking. Don't drop it, though. Okay. So metal, silver metal, is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal, and in the form of a mirror, building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, let's have a quick look. Almost there. Keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, so I'm going to take the clip off. Take out the stopper. Just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. I'm going to rinse it out a second time. Rinse it out a third time. There we go. And I'm just going to put that on, just dry this off, and put the clip back on. And if you'd like to just give that a little polish. There we go. If you'd like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go. I'll just stand there. Okay, what I'm going to do is give that to you as a souvenir to take home, and you can go back to your seat. Let's have a hand for our volunteer. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask, I have a solution of sodium acetate. And this sodium acetate's a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. But it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens as I pour the liquid onto the crystals. So I think you can see there the liquid, as soon as it touches the crystals, is turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application, and this is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, would like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And we can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool, and they'll stay as a liquid. It'll stay like that for weeks or months until I'm ready to use it again. I can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Okay, here it goes. Okay, so that's a chemical reaction that involves a change of state.
All right. I'm glad that worked. Let's go to the next slide. All right. So solids can form from the examples that we saw in this video can form from liquids. And it doesn't have to be a straight precipitation reaction. The silver coating on the inside of the flask was a type of precipitation. We turned that silver that was dissolved in solution into a solid. The solid that was formed from the sodium acetate is simply a solid formed from a change of state. We often classify that as a physical change, but a chemical reaction at the molecular level does occur. So the precipitation reactions we're going to study are those in which we have two solutions of ionic substances dissolved in solution, and then when we mix the solutions, the ions from either side, the cations, can interact with the anions from the other solution and vice versa, and sometimes they get together and form an insoluble product. And this is one example. We call it a precipitate. Oh, got another video. Let's see if this one will work.
There's two Erlenmeyer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid or salts on the bottom. I'm going to make solution, an aqueous solution with these. So I'm going to make aqueous lead nitrate here. Mixing, you can see that it makes a solution. And it does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Hopefully I don't make as much of a mess. This is the Ki, adding some water. Also making an aqueous solution. And both of these solutions or both of these salts are soluble in water. So as I stir, and I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. The nitrate ion is NO3 minus 1, and anything combined with a nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low, so it doesn't attract other ions in a crystal as strong as others. So its lattice energy is lower, and it's easy for water to pull apart the ion and have those molecule ion attractions that make this a possibility. Same thing with Ki. You have potassium iodide, and you have Ki ions that are free in this aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodine, like most halides, are also soluble because they're a -1 and they're also a big ion. There's some exceptions with those, and we're going to see that one right here. So I'm going to pour these together and take two aqueous solutions and see if a precipitate results. Now, precipitate is when a solid comes out of the solution because we're going to do a double replacement, or something called a metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2, or lead-2 iodide. And that is going to create a precipitate because the lead iodine prefers itself more, or attracts itself more, than water. So let's do that. Here we go. Very brilliant reaction. And you see that as pretty, very pretty yellow precipitates. A lot of yellow lead paints have been known to be yellow, and also a problem. So there you go, and there's your precipitate. And it's a precipitate because I know that I cannot see through the solution anymore. And if we let this settle for a while, we'll get something like this. This is a reaction I did about an hour or so ago, and you can see here that the clear solution is the potassium nitrate ions, or the potassium and nitrate ions, and the solids are at the bottom. That's settled at the bottom. All right? So there is your precipitating reaction.
All right. Okay, so the reaction that he was describing there was this one. Lead to nitrate. Lead has a 2+ charge. Nitrate has a -1 charge, so we need 2 of them to balance that. These are each plus and minus. Those are written correctly. This one is written correctly because that's a -1, and this one's still 2+. And this one's a +1, and that's a -1. But you can see that the reaction is not balanced, right? Because we have 1 nitrate over there and 2 over here. So if we put a 2 there, that gives us 2 nitrates, but it also gives us 2 potassiums. So now we have to come back over here and put it that one, and that gives us 2 potassiums plus 2 iodines, and that equation is balanced now. Okay. The solutions that we're discussing in this chapter and in the future have water as the solvent. That is, it's the major component, and it dissolves, things dissolve in it. Water is often called the universal solvent. That's a bit of a stretch, right? Water won't dissolve everything, right? I mean, here's evidence. It won't dissolve lead-2 iodide because it drops out of solution. But water does dissolve a lot of things, especially those that have that are ionic and don't form precipitates. So everything else dissolves readily in water. That's one class. There's another class of compounds that dissolve readily in water, and those are the compounds that do not form ions, but are what we call polar. They have a positive side to the molecule and a negative side to the molecule, but not a complete redistribution of charge. The electrons like to spend more time on one side than they do on the other, and that gives you a slight difference in charge, and water is attracted to those. Now, what we're trying to show in this slide is why that happens. Water is a polar molecule, right? It's made up of oxygen and two hydrogens, right? This shows a bond. It's a single bond between the oxygen and the hydrogen on either side. And the nature of the molecule is such that it is bent. It has these hydrogens over here, this oxygen here. It also has some electrons that we call lone pair electrons. In other words, they don't participate in any bonds. They still belong to the oxygen, right? And this combination of these lone pairs, which are negative, right? These are negatives. And the difference in attraction of electrons from toward oxygen and away from hydrogen. And we often represent that with an arrow that looks like this. This shows you the positive end. So that means this side of the molecule is slightly positive. That's why I use this Greek delta. It doesn't mean a complete positive charge. We haven't transferred electrons. There's a slight positive charge on this side. And on this side, there is a balancing negative charge. So overall, what we see in the water molecule is this unequal distribution of electrons. And that gives us a slight negative charge on one side, slight positive on the other. That makes the molecule polar. It has a negative pole and a positive pole. That helps it break apart ionic substances and put them in solution. A large number of them. Some of them are more resistant, like our example here. When water is, if it's pure water, what you'll see is water molecules orienting themselves with this negative side here, and you get an attraction between the water molecules. That's why pure water boils at 100 degrees Celsius and not at minus 20 or minus 30 degrees Celsius, like all the other hydrides in its group, right? The chalcogen group, which would be sulfur, right? You could have sulfur, or you could have selenium, or you could have tellurium, right? These are in the same group as oxygen, but their boiling point is very, very low. The difference is something we call hydrogen bonding. And it only happens when hydrogen is bound covalently to oxygen, nitrogen, or fluorine. Now, there are reasons for that happening, but this course is not going to dig into that one too much. Just recognize that it's a special kind of bond that increases the attractiveness of one molecule for another. Okay, it also increases the ability of water to pull ions out of a crystal. And I think I've got an animation coming up. I hope I do. Okay, this animation shows you sodium chloride crystal. We have sodium ions and chloride ions in a network of positive and negative charges. And in comes a water molecule. Okay. The negative side of the molecule, where water is located, is attracted to the sodium, and pulls it out of the crystal. Now, we're only showing 4 water molecules here, but what we actually have is we have oxygen attracted, the oxygen side of water attracted to the sodium, and then the positive sides of the water molecules over here are being pulled on by other water molecules out here in solution, which provides the force that's strong enough to pull that sodium ion out of the crystal. And then chloride ions are also removed in a similar fashion, only now it's the positive side of the molecule that's attracted to the chloride. And it keeps doing that, right? Remove one, opens a fresh surface, more water molecules rush in and continue to break that crystal apart. Now, there's something called, this idea called saturation. Every soluble solid has a limit to how much you can put into a given amount of solvent, in our case, water. And when it reaches that point, it becomes saturated and it won't hold anymore. And these values, how much can be dissolved in a certain amount of solvent, are experimentally determined. All right. So what happens when an ionic compound dissolves in water? Well, first, recognize that pure water is an electrical insulator. That's what's shown on this slide. On the left-hand figure over here, see, I can't see my arrow. There it is. This left-hand figure shows that water is an insulator. In other words, in order for that light bulb to light, we need to complete the circuit, right? Electrons will not flow in a circuit unless it's a complete loop. And if water is an insulator, then we can't move electrons from one electrode to the other through water. But when we add mobile ions in there, now they can carry the charge from one electrode to the other, and the light bulb now lights. Those substances that can do that are called electrolytes. A strong electrolyte this is a operational definition, right? If we look at the light bulb, you see the light bulb is very bright. Strong electrolytes completely dissociate in water, or nearly completely dissociate, giving you lots of mobile ions. So we get a good circuit connection between the two electrodes, and the light bulb is very bright. Let's see, are we going to talk about the others? I better. A weak electrolyte is one which does not dissociate very much. Just a few mobile ions are allowed to migrate into the solution. And that way, you get a weak connection between the electrodes, and the light bulb is very dim. But they're both electrolytes. One is strong, one is weak. Okay. So here's another example where we have potassium chromate dissolved in water. And what you'll notice is all potassium compounds are soluble in water. Doesn't matter what the anion is, put it with potassium, it'll dissolve. This reaction is occurring between potassium chromate and barium nitrate. All nitrates are soluble also. You put anything with nitrate, make a compound of it, and it will dissolve in water. So both of these solutions, separate from one another, are soluble. And they produce, as shown in the illustration, potassium ions and chromate ions, or barium ions and nitrate ions. Then when we put them together, because those ions are separate, now they have the opportunity to interact. So potassium and nitrate interact, and they are soluble because both potassium and nitrate compounds are soluble. The potassium and the nitrate are what we call spectators. In other words, they don't participate in the precipitation reaction. They're there as both reactants and products. The barium ion is attracted to the chromate ion and it forms a solid. Let's see, go to the next slide, please. There we go. What we're demonstrating here in this little table is how to determine what your precipitate looks like. Right? We've got one compound on the left. We have the cations, potassium and barium on the left, and then we have nitrate and chromate across the top. And where they meet, they form a compound. And then you have to decide which one of these compounds is soluble, which one's insoluble. And I'm going to show you how to do that in just a minute. We can do this because those ions are free in solution. Until we put the solutions together and they meet, then we show the combinations down here, the bottom. All right. These are all the possible interactions between the positive ions and the negative ions. Right? Those two reactants combine and form these products. Potassium nitrate out of solution is a white solid, and barium chromate is a yellow solid. And we find out that the barium chromate, we get a yellow solid, so we can say, all right, it's not potassium nitrate, it must be barium chromate. Okay, these are the rules for determining solubility. Now, you don't have to memorize these. I'm just putting these in there for general information. Since you're not chemistry majors, it won't do you much good to memorize them, unless you just want to. That's fine. And then notice they're in order, 1, 2, 3, 4, 5, all the way down. And they're in order for this reason. If you have a situation where you say one of these rules is conflicting with another rule for determining solubility of a product, right? Say you have rule 1, you have a nitrate on one side, and you have, say, I don't know. Let's move down. Say you have sodium, potassium, ammonium. Well, that doesn't work either. How about we have chloride salts, okay? So we have most chloride salts are soluble, right, with these exceptions. And then you say most sulfate salts are soluble also, with these exceptions. And if you have a situation where you have to decide and say which one operates, chloride or sulfate, the one above takes precedence. So it's a tiebreaker. Now, this little comment at the bottom, when we say slightly soluble versus insoluble or moderately soluble, that is true. But for this course, that's a little too much sugar for a dime. In other words, we can't afford to go into that much detail, that much rigor in this course, because it's just an introductory course. But just recognize the fact that when we say soluble versus insoluble, there's a gray area in between. And most insoluble compounds are at least slightly soluble. Right? But for practical purposes, you can treat them as soluble and insoluble. And you'd have to take my 2-semester course to actually learn how to quantify that solubility. So we've taken all of these rules and put them into a chart. So here's what the chart looks like. And there's a copy of this in Brightspace. We've got the rules at the bottom, just as a reminder, but what we have up here is cations across the top, anions down the left, and you just pick your cation, pick your anion, like let's say barium here, barium, and you go down until you find the anion. Barium iodide is soluble because the square is clear. If we keep going down from barium, say barium, and we go down to say sulfate, that one is insoluble. All right. So if you've ever had, or if you know anybody that's ever had a barium enema, right? They give you they squirt a solution of barium into your lower intestines, and then they take an X-ray because barium is a huge atom, and it absorbs X-rays very efficiently. That way, they can see the outline of your gut more effectively and determine if you have any abnormalities in there. Well, the reason they use barium sulfate is not just because it absorbs X-rays, but because barium sulfate is very insoluble and it won't dissolve in your body fluids and contaminate your body. So when they're finished with it, they allow you expel the barium sulfate and wash yourself out, drink lots of water, lots of fiber, and get cleaned out. Okay, so that's how you determine solubility. Once you find out you have a cation and an anion to assess, then you take those two and you follow them down where they intersect and see if it's gray or clear. And this is one of those useful information that will be available for exams. All right. I'm not going to go into a lot of detail here because this is for interest, the interest of those who want to go in more depth. But we're going to move on. So how to predict the precipitate when the solutions of two ionic compounds are mixed? Well, you write the reactants, right, to get the reactants written correctly and how they exist in their respective solutions. And also recognize that when a ionic solid dissolves in aqueous solutions, we're going to restrict our discussion to aqueous solutions. When it dissolves in water, those ions break apart. Now you have those free-floating ions available to interact with any other ions you choose to put in there with them. And then you consider the various combinations of positives and negatives and see whether it gives you a precipitate using your chart. Okay, so here's an example. Let's see if we've learned anything. Which of the following ions form compounds with lead 2 plus that are generally soluble in water? Okay, these are our selections. Okay, which one of these ions form compounds with lead 2 plus? Well, notice that we've got sodium plus down there. Sodium and lead don't form a compound because they're both cations. So we can throw sodium out and just look at the others. So we say, all right, what are the possibilities? Well, we have lead 2 plus. And sulfur 2 minus. So it only takes one of each to make that compound. Another possibility, we have lead 2 plus and chloride 1 minus, which means we need 2. Then we have lead nitrate, which means we need 2 of those. And we have sulfate. Lead, sulfate. This is a 2 minus, this is a 2 plus. That's good. -1, 2 plus, 2 plus, 2 minus. Okay. Then we go to our chart, and the rules that govern the chart say that this compound is soluble. This compound is not. This compound is not, and this compound is not. The only soluble one in there is the nitrate. All right? How about this one? Sodium phosphate solution and a lead 2 nitrate solution. Put them together. All right? We have, now here's a case where we have the compounds are named, but you can't do anything with them unless you know how to write the compound formula, right? And you've already learned how to do that, I hope. If you haven't, then you're in big trouble. Sodium phosphate. That's a 1 plus charge. Phosphate is a 3 minus charge. So that means we need 3 of those. And this is aqueous solution. Then we combine that with lead 2 nitrate. It says lead has a 2 plus charge. Roman numerals tell us lead is a 2 plus. And nitrate is a -1, which means we need 2 of those. And that's also aqueous solution. Okay? Now, when we put them together, what combinations can we produce? Well, if we say sodium with phosphate, that's already soluble, right? Or lead with nitrate, that's already soluble. So it doesn't make any sense to talk about these combinations. We talk about the swap combinations. Sodium interacting with nitrate. We find that that is soluble. All right. And then we have lead interacting with phosphate. So this lead 2 plus is interacting with phosphate 3 minus. So how do we balance that one? Well, we cross multiply. Put the 2 over here and put the 3 over there. And we find out from our solubility chart that that one is the solid. There's your solid right there. Okay. Now we've got a mixture of ions. We don't know where they came from. They're in solution, and we want to find out from this mixture how many different solids will form. All right. So let's use that table. Since we don't have a defined chemical reaction, we just have these cations and anions, then let's set it up like our solubility chart and put the cations across the top. So we have lead 2 plus. We have potassium. We have silver. Any more? That's it. That's all the positives. Then down this side, we have nitrate. And we have chloride. And we have sulfate. And we have phosphate. Okay? So we have a grid set up. And what do we get here? Well, with nitrates, you can look it up in your chart, but all nitrates are soluble. So this forms aqueous solutions. All right. Potassium, as the cation, always forms solutions also. So we know that interactions of potassium in these ions will form aqueous solutions. Okay. We also know that most chlorides are soluble. Let's go back. Go back to our chart. Well, it's not going to let me. All right. All right. How many different solids will form? Well, it says 6 different solids will form. Let's see if that's true. If we look at the solubility chart, right? I've got a copy of it right here. And we say, all right, how about lead? Okay, we find lead 2 plus and we follow down nitrates, chlorates, perchlorates, acetates are all soluble. Everything else is insoluble. These anions are only, we've identified this one, the rest of them form solids. Okay, how about silver? I know silver chloride is a solid, right? We proved that earlier. And if we follow silver down to, let's see, here we go. It also forms solids with these compounds, with these anions, right? So there we have 6 different solids form from this combination. The rest of them are soluble. Let's see. Chloride, sulfate, phosphate for lead, yes. Chloride, phosphate, sulfate for silver, yes. All right. Now, I mentioned that when these ionic solids are in solution, they're not really acting as molecules. This molecular equation, we call it, is the way this one happens to be written. This balanced equation of potassium chromate, barium nitrate react to form barium chromate and potassium nitrate. We write the equation that way because it's easier to balance it that way. But once the equation is balanced, then we can split it out and speak of it in terms of its real chemical reaction. All right, so that's what we're going to do next. This is actually, molecular equation is a misnomer. These do not form molecules. Molecules are bound so tightly that they act as a single unit. These things are not bound tightly enough to do that. They break apart into ions. So molecular equation is not a proper term. What we should say is, for this one, let's write it up here. Potassium chromate is soluble. And then barium nitrate, barium nitrate is soluble. And when we swap partners, we get barium chromate, solid, plus potassium nitrate. Okay? This should be called the formula equation. Okay? That's an accurate term. Molecular equation is misleading. All right. Shows the complete formulas of reactants and products and is the one we use to balance the equation. So here's what actually happens. In solution, I'm going to move this over here. We have the complete ionic equation. So once this breaks apart into cations and anions, we have 2 potassiums. and we have one chromate. We have one barium. These are all in aqueous solution. And let's see, two nitrates. Notice that when we break these formulas apart, the subscript becomes the coefficient, right? Because you have to have the same number of ions here and here. So we take that 2 and make a coefficient out of it. Then on this side, the solid remains intact. It does not change, right? Because it's bound tightly together and it's dropping out of solution. But we also have 2 potassiums and 2 nitrates in aqueous solution. Okay. So that is our complete ionic equation. And the rules for balanced equations still apply. We want the simplest whole number ratio. And it appears that since this has a 1, a 1, a 1, then we can't reduce it any further. That is the simplest whole number ratio. And this is known as the complete ionic equation. Notice one thing. This one and this one are on both sides of the equation. Right? What does that mean? Well, whether you're talking math or chemistry, if you've got the same terms on both sides of the equation, they cancel out. Right? So if we do that, what's left over? What's left over we eliminate the spectator ions. These are spectators. They're called spectators because they don't participate, right? They just watch. We get barium and chromate together to make a solid, but the potassium and the nitrate don't do anything except they're in solution, yes, but they don't participate in the driving force for the reaction. So if we eliminate those spectator ions, what we end up with is the net ionic equation. Right? So if we cancel out these, we're left with chromate plus barium yields barium chromate. Okay? And that's the simplest whole number ratio for that reaction. Now, before we do the concept check, what's the advantage to looking at the reaction in this form? Besides the fact that you're defining that this is how the reaction is driven to products by the formation of the solid. The other advantage is if I don't have barium nitrate on my shelf, then I can go to my chart and say, all right, what else can I make out of barium? Well, there's barium chlorate, barium perchlorate, barium acetate, barium chloride, barium bromide, barium iodide. All of those compounds will put barium in solution. So if we don't have the nitrate, the barium nitrate, then we can conduct this reaction with a different compound as long as barium is in it and is soluble. We could do the same thing for chromate, right? Look up chromate. All right, let's see, chromate. Here we go. Well, the only 2 compounds that are soluble, actually 3. 3 compounds of chromate are soluble: potassium, sodium and ammonium. So if we don't have potassium chromate, we can use sodium chromate or ammonium chromate, and we'll get the same result right here. Right. That's the practical advantage to identifying identifying the net ionic equation. Okay. So here we have a situation where the instructions are to write the correct molecular equation, which should be formula equation, the complete ionic and the net ionic equation for the reaction between cobalt-2 chloride and sodium hydroxide. All right, so let's do that. I'm going to leave these terms up here. We're just going to change the players. Let's see how we're doing on time and topics. All right, I'm going to have to move it along pretty quick. So here we have another word problem where we're given the names of the compounds, but not the formulas. So you have to know how to write these formulas. We're going to react cobalt-2 chloride. Cobalt-2 chloride. So that means 2 here. With what? Sodium hydroxide. So what are the possible combinations? Well, we can have sodium reacted with chloride. Right? Sodium reacted with chloride. We know that's aqueous. And cobalt reacted with hydroxide. Right? And we know from our chart that that's probably insoluble. Let's be sure. Okay, I found cobalt. I go down to hydroxide. Yes. We are forming a solid there. Now we need to balance the equation. The nice thing about these precipitation or double replacement reactions is they're very well behaved. We need 2 hydroxides. Right? 2 hydroxides. Now we need 2 sodiums. Right? And we got 2 chlorides, and 1 cobalt. That equation is balanced. Now, if you prefer, you can set it up with the budget method and confirm. But that is balanced. And that's the complete ionic equation. Now let's write, that's the formula equation. Now let's write the complete ionic equation. We've got 1 cobalt in aqueous solution. We have 2 chlorides. We have 2 sodiums. And we have 2 hydroxyls. Right? 2 sodium, 2 hydroxyls. And that yields 2 sodiums on the product side and 2 chlorides plus 1 cobalt-2 hydroxide. Okay, that's the complete ionic equation. Then you identify the spectators, the terms that are the same on both sides. Right? Let's see, there's the rest of it. Cobalt, we can't do anything because it's part of the solid. Hydroxide is part of the solid. The chlorides and the sodium are spectators. So the net ionic equation is cobalt plus hydroxide yields cobalt-2 hydroxide. There we go. Okay. That's how it's done. Very methodical, building on what you've learned in the past. All right. We talked about double replacement reactions that produce a solid, precipitation reactions. Now we want to discuss, let's see, yeah, that's better. Acid-base reactions. And in order to talk about acid and bases, we need to define what we mean by an acid, right? We've looked at acids in the past when we were learning to name compounds, how to name acids. But we're going to start with the Arrhenius definition. The Arrhenius definition of an acid is any molecule that has at least one hydrogen that can break away from the molecule. So that's just a generic part. It could be chloride, it could be nitrate, it could be sulfate. And for sulfuric acid, we actually have two hydrogens that can break away. Now, the first one breaks away really, really well. Second one doesn't break away so well. But if we try this in aqueous solution now, this is hydrochloric acid, then it's going to break apart into those ions. Now, I need to emphasize that this is not what actually happens, because hydrogen ions, which in this case would be a proton, right? Hydrogen is a proton and an electron. So if we take the electron away and leave it with a positive charge, this is just a proton for most of them, right? Not counting deuterium and tritium. Okay, so what actually happens is in this solution, in this aqueous solution, water becomes a reactant. So we have hydrogen chloride or hydrochloric acid plus water. And now this proton is transferred over and it leaves its electron behind. So there it is right there with the chloride. And this one, instead of a free proton, we actually get a new polyatomic ion called the hydronium ion. This is the chemistry. That's what really happens. But for calculation purposes and for discussing reactions, this method where we ionize to hydrogen ions and chloride ions is sufficient. I mean, it works. I just wanted you to know what the reality was before we started oversimplifying. All right. And this is a strong acid, which means it's also a strong electrolyte because it completely breaks apart and produces these free ions, right? This is essentially all one way. Arrhenius bases, that's an acid. Arrhenius bases is any formula that has a hydroxyl group within it, such as sodium hydroxide, right? Or potassium hydroxide in aqueous solution. Now, what these do, these are covalent compounds, so they have to ionize. They have to produce ions from their molecules. But these are ionic compounds. That's a sodium ion, that's a hydroxyl ion, potassium ion, and hydroxyl ion. All they have to do is dissociate in solution. And this is what they actually do. They make sodium ions and hydroxyl ions, or potassium ions and hydroxyl ions. Okay. These are definitions that were proposed by the scientist Arrhenius. He's given credit for it. And they cover over 90% of the types of acids and bases you'll encounter. And notice the hydroxide is always combined with a metal. And they completely dissociate. So they form strong electrolytes. Now what we can do is combine an acid and a base, right? Have two separate solutions, put them together, see what happens. This is one of the driving forces we talked about earlier, right? The formation of water, Arrhenius acid base reaction. And so our example would be, say, hydrochloric acid, a complete formula equation, and sodium hydroxide in aqueous solution produces sodium plus chlorine. And we know that's soluble. Oops, aqueous. Plus water. Okay? Sometimes the formation of this compound will precipitate. Right? And then you could have a combination. You'd have an acid-base reaction forming water. You'd also have a precipitation reaction for forming a solid. And those both would be driving forces for the reaction. But we're going to keep it simple. In this case, the product is water. The products are water and a soluble salt. We call this salt. Not because it's sodium chloride, table salt, because it's the product of an acid and a base. The cation plus the anion makes a salt. This is a chemical definition. That's what a salt. So any combination of, in this reaction, of a cation and anion will produce a salt in chemical terms. Okay? Now, if this is soluble, then what we get is a net ionic equation where the sodium ions, chloride ions, cancel out and leave us with that's the net ionic equation for all acid-base reactions. Assuming we don't form a precipitate. So we're going to keep it simple. We're going to say we're not going to form a precipitate here. So what's left over is hydrogen ions, hydroxide ions, and water. And this is why I said it don't necessarily need the hydronium ion here, because the mechanics and any calculations that follow from this reaction are going to be the same whether you use hydrogen ions here or hydroniums. It doesn't matter. This is an acid-base reaction. Okay. Common strong acids, hydrochloric acid, nitric acid, sulfuric acid. We left one out, perchloric acid. And actually, perchloric or chloric acid. They're also very strong. It essentially completely dissociates in aqueous solution. A strong base, similarly, dissociates into the metal ion, a metal, and the hydroxide ion, and releases all of its hydroxides into solution. So the net ionic reaction always produces water. The other is called a salt. The other product, you have water and a salt, are always the products of an acid-base reaction. Let's see. How about this one? What's the net ionic equation for this reaction? It's kind of a trick question. Right. There it is right there. It's the same net ionic equation for any acid-base reaction. Oxidation reduction reactions. Okay, we mentioned one of the driving forces of reactions can be transfer of electrons. All right? And when electrons are transferred, we identify that reaction as oxidation reduction or redox. Okay? Our example here is magnesium metal and oxygen gas. We transfer electrons from the metal to the nonmetal. That's always the case when you have ions involved. And you form a magnesium 2 plus ion and oxygen 2 minus ion. Right? Now, I will say this. We're going to try to keep it simple and transfer electrons from metals, which love to give up electrons, and nonmetals, which love to receive electrons. That is a valid oxidation reduction reaction. But you can also transfer electrons in between compounds or elements that are part of covalent compounds where you don't have any metals. Right? We may or may not get into that in this course. So one way to determine whether you have a redox reaction is, do you have any elements on one side of the equation and that element finds itself in a compound on the other side? If that's the case, like magnesium is an element on one side, it's in a compound on the other, you know instantly that that is a redox reaction. That's what we know. That's known as a rule of thumb. Okay? So we have aluminum metal is going to transfer electrons to iron 3 plus in this compound, Fe2O3, and produce free iron metal atoms. And the aluminum now is going to have a 3 plus charge, and it's going to combine with oxygen. And now we have Al2O3. This is a reaction that's often used when railroad rails are being joined. It's called a thermite reaction. It's very, very exothermic, lots of heat. Okay. Metal aluminum gains 3 electrons. Oxygen in Fe2O3. Let's see. Oxygen doesn't change. Only the aluminum, only the iron changes. So that's what happens. The transfer is between the two metals. The nonmetal is essentially a spectator. Okay. A metal-nonmetal reaction can always be assumed to be oxidation reduction. If you have a metal element and a nonmetal element produces a compound, that's always oxidation reduction. Now, we didn't find, hold on a second. We just talk about this as if these terms are intuitive, but they may not be. So I use this acronym. Actually, it's a mnemonic device. It's called oil rig. Oxidation is loss. And what we mean by that is loss of electrons. Reduction is gain of electrons. Okay. So when we have a reaction here, let's see, aluminum, iron, Fe2O3 plus aluminum metal. This is a solid. And this reaction gives us iron solid plus Al2O3 solid. Okay? These are zero charge, right? They're neutral. They have the same number of electrons and same number of protons. This one's neutral. Over here, though, this is a 2 minus and this is a 3 plus. And over here, this is a 3 plus and this is a 2 minus. So what transfer has taken place? Well, if we go from this iron to that iron, how did it get from a 3 plus to a 0? We need 3 electrons to neutralize the 3 plus. So this gained 3 electrons for every iron, right? We've got 2 irons here, times 2 equals 6 electrons were gained. And gain means reduction. So the iron was reduced. One of the main rules of oxidation reduction reactions is you can't have one without the other. They always occur together. And the other one goes this way, right? This is a loss of 3 electrons per aluminum, but we got 2 aluminums times 2 equals 6 electrons. And this is oxidation. Reduced or oxidized. So the aluminum was oxidized and the iron in this compound was reduced. Okay? Notice one other thing. In a balanced equation, the number of electrons gained has to be the number lost. That must balance, or your equation is not balanced. All right. So that's a crash course in oxidation reduction reactions. We don't have time to go into more details here. We just have to leave it at that example. But that field is broad. Okay. Driving forces we've studied so far. Form solid, form water, transfer electrons. How about a gas? Formation of a gas. Okay. Precipitation reactions. If there's a solid formed from 2 solutions, you have a precipitation reaction. It's also a double displacement reaction. When we start classifying reactions, sometimes they fall under more than one category. So this reaction is a double displacement reaction. It's also a precipitation reaction. Acid-base reactions, we know the net equation is hydrogen ions plus hydroxyl ions equals water. Water is always formed. Oxidation reduction, always transfer electrons. Here's another example of a metal and a non-metal. So These types of reactions are easy to identify without writing them on the board. Lithium's a metal. It's going to lose electrons. It's oxidized. Nonmetals will accept those electrons. They are reduced. Formation of a gas. I used this one earlier. Hydrochloric acid and zinc forms hydrogen gas. It's also an oxidation reduction reaction. Notice that the zinc on the reactant side is neutral. It's a neutral metal, but it's in a compound on the other side where it has a 2+ charge. So it had to be oxidized to get there. So this gas formation reaction is also an oxidation reduction reaction. And it's a single replacement reaction. Why? Because the zinc replaced the hydrogen. Notice zinc and chlorine now are together on the product side, and the hydrogen is off by itself. Okay. This is a general schematic for classifying equations. Use it if you think it will help. Another one that we haven't talked about is combustion reactions. Combustion reactions always have one specific reactant, oxygen. You can put anything over here, but it has to have oxygen to be a combustion reaction. And it's also a redox reaction because that oxygen is going to end up in a compound, right? Element to compound, it's oxidation reduction. Example. We use methane. We get carbon dioxide and water, right? And then we can balance it, right? We say we have, let's see, how about 2 of these? That'll do it. Now this one, oxygen it lost gained electrons, right? Because it's 2- on this side, 2- here. And hydrogen didn't change, but carbon in this one is a 4-. Now, I'm using a procedure called oxidation states. This is an illustration also of the fact that oxidation reduction reactions can occur between nonmetals. Nonmetal, 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 nonmetal. So we don't actually have a charge here, right? Because methane is like this. Doesn't form ions. Doesn't have any ions in its mixture. These are covalent bonds. So we use a procedure called oxidation states as a budget method for following the electrons. But the point is that if it has oxygen in it, it is a combustion reaction and it is automatically oxidation reduction. Oops, I messed up. Wait a minute. Oh yeah, this does have to have 2. Right, there's 2 there and 2 there. My mistake. Okay, another way to classify is synthesis reaction or combination. We've looked at one of those already. We take elements or simpler materials and form a more complex material. Our example was sodium solid and chlorine gas makes sodium chloride. That's a synthesis or a combination reaction. There's another example. Carbon plus oxygen yields carbon dioxide. These are also, well, this particular one is an oxidation reduction reaction. It's a special class of synthesis. Decomposition goes the other direction. You take a more complex substance and break it apart. Like we electrolyze water. We take water and split it into hydrogen and oxygen. That's also oxidation reduction. We know that because you got elements on one side and compound on the other. And this is another flow chart to help you organize your thoughts. If it helps, great. Let me see. Where do we stand? Yeah, we're good. We're coming down to the end, and I got 20 minutes left. So let's look at this last one, and we'll be done for the day. Let me see. Okay. This is Thursday. Next Tuesday, I've scheduled as a buffer day. So I'm going to, next Thursday, I'm going to jump into the review document and start working problems out of the review document. And if it takes two sessions, I've got identified, let's see. Yeah, I've got next Tuesday and Thursday identified. Tuesday is a buffer, Thursday's a review day. So I've got two sessions where I can talk about reviewing the material. If we finished everything on Tuesday, then Thursday will just be a tutorial session. All right, back to the topic. Reaction between hydrogen and oxygen to form water is this. That's a balanced equation. That's the reaction that takes place in a lot of rocket engines. We can classify this reaction as what? Well, it's got oxygen in it as a reactant. That's a combustion reaction. It's also an oxidation reduction reaction. And it's also a synthesis. You've got two simple materials, elements in this case, forming a compound. All of the above will classify this one. Oh, that's it. I thought we had more. Okay, that's it. So we're done, and your review document will give you lots of practice with what we've talked about last Tuesday and today, Thursday, chapter 6 and 7 for exam 4.